So we're going to be going through a few different types of our special case factoring. We've got perfect square trinomials, difference of squares, as well as sum and difference of cubes. Some of these are formulas you have to know in order to factor it. If you don't, then you can't, period. Others are ways that help you take a more complex polynomial and factor it rather than trying to use a traditional method, which would be a lot more cumbersome. So we're going to start with our difference of squares. Our difference of squares is going to be defined as a binomial where we are subtracting two perfect squares. All right? When we're dealing with exponents, any even power is going to be a perfect square. So if I have x to the second, x to the fourth, x to the sixth, all of those are perfect squares. And then if we're looking at our integers, then knowing some of your perfect squares is going to be helpful. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. Usually up to recognizing kind of 12 squared, 144 is a good baseline. That'll get kind of most of those covered. Outside of that, it's going to be a little trial and error figuring out if it's a perfect square or not. It always factors to be the same pattern. If we have two terms in a binomial being subtracted, first and last term are perfect squares. We square root both of those, and then we create two new binomials, one with addition, one with subtraction. Okay? So it's always going to factor into two different binomials. I'll get to that in a second. All right? So the square root of p squared gives me what? P. So it's going to be p plus and p minus square root of 100, 10. So p plus 10 and p minus 10. Easy peasy. All right? Now, 2x squared, is that a perfect square? No. But what's our first rule of factoring for everything ever? Always? GCF, which in this case is what? 2. When I factor out that 2, now I'm left with a difference of squares. 2 x plus, x minus, what? 3. Okay, so always check that GCF. When we're looking at terms that have coefficients and variables, we need to make sure that all factors in each term are perfect squares. So 9 and a squared, as well as 16 and b squared are both perfect squares. So we'll square root those both to set up our factors. There's that. 1 plus, 1 minus. Square root of 9a squared being 3a. So we'll have 3a plus and 3a minus. Square root of 16b squared being 4b. Split that. There we go. I'll be okay. All right, 4b and 4b. We have a binomial that itself is being squared. We can still follow our same rules. It's just going to be a little bit longer. If I square root m plus 3 squared, I'm just left with m plus 3. m plus 3. And then the square root of 49 z squared is what? 7z. Garrett, can you get the door? Okay. So we still have the plus and the minus. Okay. Nope, we still have the plus and the minus. Go back here. Okay. Y to the fourth minus 16. What's the square root of y to the fourth? Y to the second. Y squared. But alas, we are not done. Good.
Should the plus always come first?
Doesn't matter.
Wait, does it get harder than this?
I mean, does difference of squares get harder than this? No. Yep. One of our factors is still a difference of squares. So we need to continue factoring it as much as we can. So we still have y squared plus 4. That doesn't have any factoring. We can't factor a sum of squares. That's not a thing. But we can factor the new difference of squares. Y squared minus 4 splits into y plus 2, y minus 2. Yep, there's no factoring y squared plus 4. Not with real values. Okay, so that's our difference of squares. You didn't care to write anything down. You just want to take a picture.
Well, here's the thing on the terms, I'm gonna visually see it, and I'm gonna study the picture.
We'll talk about a solution to that later. Alright, perfect square trinomial. Okay, perfect square trinomial, we're following a pattern. And we're trying to kind of check to see if the polynomial fits in a certain scenario. Okay? So what we have is a trinomial. First and last term is squared. Okay? Perfect squares for first and last. The middle term is 2 times the square root of both of those. 2xy. The difference between these two formulas is 1's plus, 1's minus. Okay? Just for that first sign. They both have plus for the second sign. It always factors into a binomial squared. Okay? The only difference being plus or minus. Again, based on whether this sign was plus or minus. Here's how we check to see if a polynomial is a perfect square trinomial. We first look and notice, hey, my first and last terms are both perfect squares. If I square root both of these, square root of 49z squared is 7z. Square root of 1 is 1. If I multiply those and then double it, why do I double it? Because that's part of our formula. If that equals my middle term, then we have a perfect square trinomial. So we do that first to verify, is it a perfect square trinomial? Hey, that's my middle term. Yes, it's a perfect square trinomial. And then factoring gets really easy. 7z, 1. Take that sign and square it. Done. If it's a perfect square trinomial, you've already done half the work by square rooting x and y. Plug it in, binomial squared. You're just going to match this sign here. Perfect square, perfect square. What's the square root of 9a squared? What's the square root of 64b squared? If I multiply those and double it, do I get 48ab? Yeah. So since that's my middle term, I take the two square roots. Is it going to be plus or minus? Plus, because my first sign is plus. Done. Easy peasy lemon squeezy. Are you going to continue with every slide, or are you good?
How many questions is this test?
87.
Man.
Alright, difference of cubes. So, similar to difference of squares, but a longer formula to memorize. Okay? I have a binomial. Gentlemen, you good? We saw the binomial. First and last terms are perfect cubes. If we're looking at exponents, it's any multiple of 3, 3, 6, 9, 12, anything that's a multiple of 3 is going to be a perfect cube. And then when we're looking at our numbers, 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, okay? Those will be the most common ones that you'll see. There are others which may take a little guess and check. If you see you have these exponents, that are multiples of 3 and a number, and you're like, I don't know if that's a perfect cube or not. You may need to do some guess and check to figure out if it is or not. But we take the cube root and we just fill it into this formula. Once you get used to the pattern, it's pretty straightforward. Start by cube rooting your first and last term. So what's the cube root of x to the third? X. What's the cube root of 1,000? 10. So we're going to start with those two terms. Okay? We're going to match the sign that we have. Difference of cubes, subtraction, subtraction. Okay? That's the first part right there. The second part, we're going to take each of these numbers, okay, or each of these terms, x and 10. I'm going to start by squaring the first one, then I'll multiply them, and then I will square the second one. So if we square x, what do we get? X squared. Then we multiply them, what do we get? 10x. And then I square the second, or the last term, what do I get? 100, okay? So square it, multiply, square it, and then the difference of cubes is going to be plus, plus. I'm going to highlight the differences between the two in just a minute. Okay? And that's our factor. Boom. (8k to the third minus y to the third). What's the cube root of 8k to the third? 2k. Give myself a little more room. 2k. Okay? And cube root of y to the third is y. Am I have plus or minus? Good. How do I get the next term? We're going to square 2k. What is 2k squared? 4k squared. 4k squared. How do I get the second term? 2ky. Multiply them together. And the last term. Y squared plus plus. Cube root of 27m to the third. 3m. Cube root of 64n to the third. 4n. Be careful with 64 because it's a perfect square, perfect cube, 4th power, and 5th power. Yeah, that's a fun one. It's a fun number. Okay? Plus or minus? Minus. Alright? Next term? 9m squared, because we're going to square the first term. 9m squared. Plus or minus? Okay? Next term? 12mn. Multiply the two. 12mn. And the last one? Plus or minus? 16n squared. So we just plug it into the formula and solve. The only difference between a difference of cubes and a sum of cubes is we switch two of the signs. Those two signs switch. The last sign is always plus when we have a sum of cubes or a difference of cubes, but we're always going to match the first sign with our original binomial. The second sign is always going to be opposite. So if I have a difference of squares, the second sign is plus. A sum of squares, the second sign is minus. I also want to point out that for cubes, we have a sum and a difference. For squares, we do not have a sum. Okay? When we did our sum of difference of squares here, that did not get factored. There is no sum of squares, just the difference. But with cubes, we have both. Okay? So, sum of cubes, same idea. Square root, plug it into the formula. What's my first term going to be? Plus or minus? Plus. We're going to match it. Second term. Next term. Good. square the first term. Then what? Minus 10p. Multiply 5 and 2p, we get 10p. And last term, plus 25. We square the 5. Okay? B, 64m to the third plus 125 n to the third. First term, 4m. Okay? Plus or minus? Plus what? Next term? 16m squared minus, good, 20mn, good, plus 25n squared, good. Okay? C. Ooh. GCF. Okay, what's my GCF? 2. Okay? Now, much easier. First term. Good. Okay? Follow the pattern. Same idea here. X is just a minus 4. So when I cube root a minus 4 for power, what do I get? A minus 4. First term is a minus 4. Second term is what? B. Plus B. A minus 4 plus B. Alright. What's my next term? A minus 4 power. Okay, we'll expand that in a minute. What's the next one? So we're going to multiply these together, right? We'll do that in a minute. We'll distribute that momentarily. Last term? B squared. Okay, we can expand these. So a minus 4 squared, all right? Fun fact, that's a squared binomial, right? We can work backwards with our perfect square trinomial. If I have a binomial squared, where I have a difference, like a minus b, or a minus 4, I can go ahead and square the first term, square the last term, multiply and double them, and then I have my polynomial. You can work backwards by knowing these factoring. Part on your slide. There we go. Makes multiplying those out a lot easier. A squared minus 8a plus 16. Nothing changes with the first binomial or first trinomial. A minus 4 plus b. So a minus 4 squared expands into a squared minus 8a plus 16. Here we're going to distribute. That b will get distributed, but so will that negative. So we end up with negative ab plus 4b. And then we're left with b squared at the end. If you had any like terms, you would combine them. We don't, so we can't. So sum of cubes, difference of cubes, perfect square trinomials, and difference of squares. Those are our special case factoring. So you've got this nice little handy list here. Essentially, you need to be able to know how to use these. I will provide these, not necessarily in any particular order and not with names attached. So you kind of just have to, rather than memorize, be able to recognize, and you should be fine. But if you're like, I don't know how to use that formula, then sorry for something. So make sure that you recognize when you have those. Always check for GCF. Factor it completely. Okay. Sometimes there'll be multiple factoring steps. You need to check for those. especially with difference of squares. I remember when I used to teach Algebra 1, I would give something like x to the 16th minus 64, which ends up with like 7 factors by the end, because you get difference of squares and then difference of squares and then different over and over, and you end up with a ton of different, okay? You won't see anything that extreme, but just keep in mind you need to make sure cancel more. Questions, comments, concerns? Cool.